Hello everyone, I am Tasbiraha Othoy. Today I am giving a presentation on weak heap. So what is a weak heap? Weak heap is basically a data structure, and you can see in the right side it is a weak heap tree, and it has relaxing properties of a heap. And heap is basically a binary tree with specialized structure, you can say. So a weak heap has relaxing properties of the heap properties. So this special kind of data structure was introduced by Ronald D. Dutton in a research paper at the University of Central Florida in 1992. The structure is designed in such a way that gives a competitive sorting structure. So the structure is shown here, and the weak heap has three rules. So to know a tree is weak heap or not, you need to know the three rules, and if the tree satisfies all these three rules, then it is a weak heap tree. So the first rule is that the value in any node is at least the value of any node in its right subtree. So this is the root node, and its value is 50, and the nodes of its right subtree are 30 and the next 20. So all these values are lesser than 50, and the left subtree is 35. So it is greater than 30. So there is no condition for the left subtree, only for the right subtree. Next, the second rule. The second rule is the root of the weak heap tree has no left subtree. So you can see here, this is a binary tree. This is a weak heap tree, and the root is 50 and it has no left subtree. And as all the right subtree are lesser than the node, so the root has the highest node with the highest value. Next, the third rule is nodes with fewer than 2 children except the root node appear on the bottom two levels of the tree. So these are the two nodes at the bottom level, and both of the node has no children, that is fewer than 2 children. And as this tree satisfies all the three rules of weak heap, so this is a weak heap tree. Next, there is an important operation that is called merge operation. So in this operation, these two weak heap tree will be merged into one single weak heap tree, which will satisfy all the three rules. And so I will explain the merging operation for the tree rooted in I and J. So the merge has two steps. In the first step, the root node containing the largest value becomes the root of the merged tree. So this has become the root, and the second step is that the smaller root, that is the root with 45, becomes the right son of the larger. This is the smaller tree becomes the right son of the larger, and the original right sons become the left tree of the tree with smaller node. So this is the tree with small root of the tree with a smaller node, and is left subtree is the original one's right subtree. So this is the merged weak heap tree, and it holds all the three rules. Next, the one-dimensional array implementation of weak heap tree. So I will present this tree in a one-dimensional array 8, and this tree has 9 nodes, and so the size of the array to preserve this load will be n plus 1, so that is 10. So there will be one extra bit for the array, and all the nodes of the weak heap tree will enter into this array in breadth first search order. I have listed the order to enter this array in the tree. So this will be the array representation after entering all this node into this array. So another thing is, for this tree, each node in index I can have each node in index I has 2 children. One is indexed in 2i and another is in 2i plus 1. So you can see for node 45, one child is twice I, that is indexed in 2, that is 30, and another child is twice I plus 3, that is indexed in sorry, twice I plus 1, that is 3, so that is 22. And another interesting criteria for the 1D array implementation of this weak heap is that it has another array of same length as the primary array 8, and it's called the reverse array. I have denoted the reverse array as R, and the reverse array mainly contains, reverse array is a Boolean array, and it mainly contains the tree has either left child or right child. So basically, if a node has its left child in if a node in its twice I index position has left child, then the value of the reverse array will be false, and if the in the twice I position has right child, then the value of the reverse array will be true. So for this array, you can see node 45 is indexed in 1, and its twice I child, that is 2, is left child 30. So it will contain F, that is false, in its reverse array. So if I do the similar thing for all these nodes, then the reverse array will look like this. Next, a very important operation for weak heap trees, that is weak heap sort. Basically, the last extra bit in the H array is needed to sort this weak heap tree, because the nodes enters this extra bit position first. So for sorting a weak heap tree, you can see the first bit, the first root is the highest node of a weak heap tree. We know that. So the root will enter into the last position of the array. And now it's not a weak heap tree, so this left connection will break, and there will be small trees, several small trees. And next, 2 small trees will merge first. Like for this case 47 and 35 will merge first. Next, these 2 will merge using the merge operation for binary for weak heap tree. And next, these 2 trees will merge. So what we do, that we first unmerge the trees. We break the left connections of the trees and becomes smaller trees, and then we merge the trees again, and first the lower level trees with lower level merges first, and then the higher level trees merges. So now it's a weak heap tree, and the root has the highest node, and this node will enter the next array position. Next, again the same operation will run like this, and the root, after doing all the merge operation, the node with highest root will enter the next position of the array like this. So what you can see, that the merge operation continues unless all the small trees are merged into one tree. So like this, all the operation will conduct, and the sorting will be done, and the array will look like this. So the weak-heap sort mainly does the sorting in ascending order. Now the time complexity analysis for weak-heap sort. So this is the algorithm for weak-heap sort. The first step is the WEAK-HEAP. Next, the weak-heap tree with the larger nodes enters the array, that is the move operation, and next the merge forest function occurs until all the small trees are merged together. So for step 1, the weak-heap sort will does exactly n-1 comparisons, and for the third step, the number of comparisons will nk minus 2 to the power k plus 1, as log n is equal to k. And so if we add, the second step will have constant number of comparison. So if we add all these 3 steps, then the overall best case comparison will be nk minus 2 to the power k plus 1. So the time complexity for this algorithm in the best case will be order of n, and the overall worst case comparisons will be n minus 1 log n plus 0.086013 n. So the worst case comparison will be order n log n. So last, there is comparison of weak heap sort with other two sorting algorithm. One is quick sort and another is bottom up heap sort. So for a lower number of nodes, the number of comparison is pretty much similar, so you cannot differentiate much. But for high number of nodes, you can see that the weak heap sort need lower number of comparisons than the other two sorting algorithms, so the time complexity will be less than the other two sorting algorithm for high number of nodes. So that is all for my presentation of weak heap. Thank you everyone for watching.